long introduction on groups, just considering finite groups to introduce many definitions. And so today we're going to move to much more physical consideration. So I'm first going to give you some physical motivation. Where do we get groups, and especially which kind of group? And we're going to see that the group we are interested in physics are mostly the Lie groups. And then I'm going to give you a first catalog of Lie groups that you're going to see in your different lecture in the future. And then we're going to, in more technical detail, what is a Lie algebra, what is a Lie group, how are they related, what is their relation, okay? And so I guess for today we're going to do at least these two parts and start this one. And then tomorrow we will move to this technical detail and hopefully start with SU2 as the example we're going to see really in details, okay? So if you remember, yesterday we said that groups were related, of course, to the notion of symmetries. And in physics, we call a symmetry the mapping of the physical states of a system which leave the dynamics invariant. And so this is what we call, of course, a symmetry in physics. And then since, how can you already see that this is going to be related to group? You know that a mapping is, the composition of mapping is always going to be associative. Then there is an identity, meaning that if you don't do anything to your system, of course, the dynamic is preserved. And since the mapping are invertible, by assumption, usually the mathematical structure of a group appear quite naturally here, okay? So symmetry, of course, are very important in physics because usually it allows you to study a system which would be otherwise much more, really too complicated to say anything about it. And so usually you try to use symmetry to say something about it. So let's look at some specific cases. So here it's the physical motivation for the symmetry. And let's first look at what you will see in quantum mechanics. So let's first look at, so in quantum mechanics, the state of physical system is described by a vector in a Hilbert space using, so if you use Dirac notation, usually you use a ket to describe your physical state. And then physical observables then correspond usually to Hermitian operator. Okay, so you have your physical state, physical variable where we consider Hermitian operator. And the physical information is then encoded in probabilities. So you want to know the probability from going from state C1 to state 2. And this is given by this scalar product. So of course you have a Hilbert space, meaning that you have a scalar product well-defined, etc. So I'm not going to give too many details. You're going to have in September a course on quantum mechanics. So I just want to make sure here that we see how symmetry are going to act here. So symmetry are represented by transformations that leave the physical information. So that is here that we want to leave the probability, okay, defined above. So we want this to be invariant. So this means that if now we have a state, so if we see an observer in a state represented by C1, and then and we have another observer, we want this other observer to observe the same system in a state, then if it's another observer, it's going to observe the system in another state. But what you want to have is that you get the same probability, okay? So you want to have So let's write with probability from. So this is what you expect. Okay, so what does it mean exactly? So first, I need to add something. So Wigner, so everyone, I guess, know the name of this well-known physicist in the 30s, showed that the transformation between corresponding states of two observers can be described by an operator U, okay, such as you have, when you have two different observers, you know that you can have an operator U, and what he proved is that this operator is either linear, unitary, and linear, or you also have the possibility of its anti-unitary and anti-linear. So let's just look at this a bit. So do you remember what we need? So here, as I said, we want to talk about groups. So of course, this is interesting in some situation, and I'm not going to give more detail here. But since we're interested in group, I'm going to focus on only this case. And do you see why? What is the issue with here? What won't you get? Do you remember the definition of a group? What do you need to have?
Closeness? Closure?
Yeah, but here, and yeah, you need closure. So here, you won't have it all the time, but also you need the identity. Okay? And here, identity is unitary and linear. It's not anti-unitary. And so here you don't have identity. So here you have the identity. So of course, we're going to focus on this case because we want to study symmetry using group and not strange objects for the moment. So in this case, we're going to focus on that. So what does it mean that it's unitary and linear? So what is going to satisfy this operator? So unitary and linear. So if I look at the scalar product of, U, then this has to be equal to the scalar product of the two untransformed states. So this is a unitary definition, and linear means that, of course, if you act on this linear combination of states, then you can write this as A times U acting on the first state plus B times U acting on the second state. Okay, so this is the linearity condition. So what does it mean now that we want to preserve this probability in terms of this U operator? And what can we say about it? So this means that we want the probability conserved. So what we want is to have this equation. So I call my state and then, of course, the probability is the norm square of this scalar product. So this is what we want to preserve the physical information. We demand this equation is satisfied. So now, how can we modify this using the definition of an adjoint operator of an operator? You can rewrite this as Is that clear to everyone? Everyone knows the definition of adjoint? The adjoint of an operator? Okay, so from here, what can you say? What would be the very simple the simplest case, the simplest choice here to get that this equality is satisfied. What do you want to ask? Yeah, sure. Okay. So here, let's just ask that we get this, and this is equivalent to say that. So is the adjunct. Okay, so here you see that also, in addition, what we get here, it's already the inverse. Okay, for a group, we need the notion of identity, notion of inverse, so we already have it here. So now we need to think about what is the binary operator that we have here. So of course, we can think about the composition of the operator now. So let's consider that we have not only 2 observers, but 3 observers. Okay? So now we want to look at the composition. And very naturally, we are going to get operator. So let's consider we have 3 observers. So the first one, the second one is related to the first one using an operator U1. The second and the third one is related to the second one using but of course, then you can relate the first and third. So here, the first observer is related to the second, and the third is related to the second observer. Okay, so of course, here we can relate the first with the third one, and this would just give so here you have U3 will be defined as this product of operators. So what do we have here? You see that these operators that relate different observers, in fact, provide a representation of the group of transformation. Okay, so here you're looking at how you transform your system going from one observer to a second observer, and what you get is a representation of a group. So a group here appears quite naturally. And if this transformation, of course, is a symmetry of a quantum mechanical system that you're considering, this means that there is a representation of the symmetry of your symmetry group on this Hilbert space. Okay, so you see that the structure of a group appears quite naturally even in the quantum mechanics context. So now let's look at other examples. First, in just Newtonian mechanics, so Galilean mechanics. And this is more or less a small exercise for you. So in Galilean physics, you can have different, now we talk about inertial observers, okay, which can be related by a set of transformation. And so do you know what are these transformations? What we call the Galilean transformation. So what do you have for the Galilean transformation? So in Newtonian physics, what are the symmetry of? If you have 2 inertial observers, what are the transformations that you can perform?
X goes to X plus VT.
Yeah, so this is what we're going to call the Galilean boost, okay? So you have where you have where v is going to be the relative velocity between the two inertial observers, then what else do you have?
Time translation.
Rotation.
No, yeah, but time is absolute here, so you don't have.
It's just space rotations.
Rotation.
Yeah, you have the rotation, yeah, and the translation in space. Okay, so we have in space, and then rotation of space too. Okay, so in Galilean physics, contrary to the case we're going to look right after special relativity, where now time is absolute here. Okay, so you have transformation only on your special special coordinates. Okay, so now of course these are groups, and the Galilean transformation form groups. Okay, but can you show that? Can you see that this is a group? Is it a group or not? The Galilean boost. What do you think? Is it a group?
It seems.
Yeah. Okay. So yes, but be careful because so this is the case in Galilean physics, but right after we're going to talk about special relativity, and in special relativity you also have boost, but boosts do not form a group. Okay. And if you remember, you already had, I guess, some lecture on special relativity. The addition of velocity in special relativity is not associative. Okay, so it's also the case for the boost here in special relativity. So here, yes, it's a group, and of course you could do calculation. So if you want to do a similar calculation that will be done in the special relativity case, then you could look at this matrix acting on a 4D vector and see the composition of the velocity here. And of course, the associativity here comes from the associativity of the addition for the velocity. Then you have the unit is going to be defined when the relative velocity between the two referential is equal to 0. And then you have the inverse when you look at just minus v instead of v. Okay? So this you can quite easily see that this is a group. And so now in the case of now in special relativity we live in a 3+1 dimensional Minkowski space. And so now what are the transformation associated to this Minkowski space? So here now it's and in this 3+1 Minkowski space, what we have? We can define the orthonormal bases and a scalar product between two quadrivectors. So if I consider a quadrivector, I'm just going to fix the notation here. Then the scalar product is just given by, so it's to fix what is the signature I'm going to use. And this can be written using Einstein notation here, and the Minkowski metric, the tensor metric eta, where here it's a tensor metric given by the diagonal with 1, minus 1, minus 1, minus 1. Okay? And so this scalar product is going to be invariant under the Lorentz group. That we're going to see is SO13 in using my notation here. So it's going to be a subgroup of what we call the linear group. And more precisely, this Minkowski space here satisfies the symmetry. So the Lorentz group plus some translational symmetry. So the physics here that describes the universe must respect this symmetry, and this, the complete group is called the Poincaré group. Okay? So here, the symmetry that should be preserved is Lorentz plus translation. And this is what we are going to call. So I'm going to come back on this group very soon. And this afternoon we have a tutorial, and the tutorial is going to be really on this Poincaré group and study the Lie algebra associated. So this is going to be what all these examples are already examples of Lie groups. So I'm going to come back on that. And associated to this Lie group, you have Lie algebras. And in the tutorial, you're going to study what is the Poincaré algebra associated to this Poincaré group. So what else can I say here? So this is a symmetry group of the Minkowski space. Then which other kind of symmetry do we have? We have what we call gauge symmetries. And you will come back many times on this notion of gauge symmetry during your future lecture, because gauge theory are among, of course, the most beautiful and symmetrical law of physics and that we know today. And our current theory of electromagnetism, the strong and the weak forces, and gravity are all described with our all gauge theory. Okay? So you will see that the first three forces, so electromagnetism, the weak force, and the strong force, can be described by a kind of gauge symmetry, which is the Yang-Mills, called the Yang-Mills theory. So here you will have electro. The weak force, the strong force can be described by Yang-Mills theory. And of course, the exception is gravity, which is really apart and which is described by another kind of gauge theory that you call general relativity. And I'm going to come back very soon on this, on the gauge group associated to these forces. But so now, let's see what are these kind of groups I mentioned here. All these groups I mentioned here are what we call Lie groups. So what is a Lie group? So here, in many of the examples, so we have either a rotation that you should already know quite well, a translation, and the group element that describes this symmetry can be labeled by a continuous parameter. Okay, so the rotation could be labeled by an angle. The translation can be labeled by the vector describing your translation. So this is really the characteristic we're going to use of Lie groups, is that Lie groups are described by groups which are described by a set of continuous parameters. Okay, so this is the first kind of definition. So Lie groups described. So by a set of like the angle for rotation, a fixed vector for a translation, so more precisely, a Lie group G. So I don't know if you already seen with David some differential geometry. Have you seen some differential geometry this morning or?
Yes.
Okay. So you all know, okay, the notion. So, okay, so it's quite, no, but I'm not going to use much here. So just the definition, if it is what we call a manifold, okay, so you know what is a manifold. It's a topological space like which locally resembles to Euclidean space, okay? And you want that the inverse and operator inverse and product are smooth map here, okay? So what are these? So usually you have the inverse is going to be from G to G, and you have the product from G and these are so this is a bit more precise definition than just this definition, but mostly we are going to use this result that they are described by a set of continuous parameters. But so what does this mean, or what are the examples you could have? So for example here, which group do you know? So yes, I'm going to give you a catalog very soon, but I guess you all heard about SU2 or U1 as group. So SU2 is, in fact, can be seen as a manifold, is a three-sphere. Okay, so it's S3 here, and U1 is the unit circle, so it's really S1. Okay, so these are the example of how you see Lie group. You describe Lie group as a manifold. Okay. Okay. So any questions here? And of course, usually, so they are going to depend on some continuous parameter. Okay. And we are going to choose for convenience that this is going to be the identity. Okay. Yeah.
What does SU stand for?
SU?
The letters SU.
Here, okay. So I'm just going to give you the catalog of and give all the. So here it's a special unitary group, okay, and this is unitary. But I'm going to give now the catalog of. So SU2 and U1, we're going to study them a lot. U1 is very simple; it's abelian. But why are you going to talk about this one? Is because it's the gauge group of electromagnetism. Okay, so electromagnetism seen as a gauge theory as for gauge group U1, and because this gauge group is abelian, that's why. So here I told you that all these three different forces are described by the same kind of gauge theory, a Yang-Mills theory, but each of them is described with a different gauge group. And the fact that this gauge group is changing is going to make that this theory is more or less complicated. And of course, the case of electromagnetism is described with U1, which is an abelian group. So this will make that at the end, the Yang-Mills equation, our linear equation, are well-known equations that we know how to deal with. But for example, in the case of the strong force, where you will have SU3, okay, then the equation here are going to become non-linear because you have a non-abelian group, and everything is much more complicated. Okay, so you see that the framework is going to be the same, But what is going to make things change is really going to be this symmetry group that you have, the gauge group that you have. And so that's why now we're going to see what are the different gauge groups that you are going to be interested when doing physics. Okay? So let's maybe move here. So before giving you any definition, since when I'm going to give you definition and or theorem, and I will use examples, it's better that you know what I'm talking about. For example, this kind of question, what does it mean SU2? I prefer not to have it all the time, so I'm going to give you a catalog of what are the main Lie groups that we are going to use in physics, and these are the Lie groups I'm going to use as examples to illustrate the technical concepts that we will introduce later. Okay? So this is the first part about, so it's kind of So I'm first going to introduce a notation. I'm going to use, so this is a set. We are going to consider only groups which are matrix groups. So let's just introduce what is the set of matrices with real or complex entries. And here, when I write this k here, this means that I'm not specifying if k is equal to c or k is equal to r. Okay, so in some of the example, I will have to specify that we are in the complex case or in the real case, but when I don't need to specify it, I'm just going to use k. Okay, so this is not a group yet. What do you need to have a group? So the first group is going to be what we call the general linear group, and here I can keep, I don't need to specify if it's real or complex. So do you know what is this group? So here it's what we call the general linear group. So it's the first group you can build using matrices. So anyone know what do you need to have here to have a group? Which restriction do you need to have on the set of n times n matrices? Yeah. Okay. So this is exactly what is this group. You need to have invertible matrix. So it's just the set of matrices that has. How can we characterize an invertible matrix? We can say that its determinant is different from 0. Okay. So this is just the set of the group of all invertible n times n matrix with k-valued entries. So it can be real or complex. Okay, so now do you know what would be the special linear group? So here this means special. Do you know what we add? So here, for example, I told you that this was for unitary and then special unitary group. So what does it mean when you add this special?
Determinant
equals 1.
Yeah, is equal to 1. Okay? So here it's a set of matrices with determinant equal to 1. So of course, if determinant is equal to 1, it's different from 0, so it's invertible. So it's a subgroup of the general linear group. So here, and you can think about this group as a group of all volume-preserving linear transformation of, in the case of k is the real numbers, okay? When k is, it's R here. It's a group of all volume preserving linear transformation of course here. If it's n-dimensional, it's mean Rn, okay? Okay, so now, so here I told you that it's a group of all volume preserving linear transformation, but usually we are interested on groups that preserve distances and angles. Yeah?
Isn't it determinant n is 1? Or?
Yeah, thanks. Of course, yeah. Thank you. Okay, so what would be this group? It's what we call the orthogonal group. And I'm going to use a general one here with PQ. So this means that it depends on the... So have you seen already the notion of metric or this morning? This morning too? Okay, so on Rn, you know that you could have different metrics. For example, already in the space-time we have, so you know that when you're Euclidean, you just consider, this means that you don't specify what is time and space, okay? You consider all at the same level, but then already we have the Minkowski metric, which has a signature. Here I've chosen 1, -1, -1, -1. But so in Rn, so this is in R4, okay? It's 4-dimensional. But in Rn, you could also choose the same with a metric with P plus 1 value and Q minus 1 value, okay? And this will be your metric, and then from this metric, you can define a scalar product. And then associated to this metric, so you know that you need the metric to compute distances and scalar product. So using this metric to compute the distances and scalar product, this group is going to be the group that is going to preserve the distances and angles. Okay? So this means that you need this orthogonal. So this is what we call orthogonal group. But so more specifically, let's first maybe go to the Euclidean case, where you don't have this signature, and then you should know more. So here it's when you have, yeah, I'm not going to give you too many details. So the details for this group are in the lecture note that I'm going to post. I don't think it's really useful for you to know more now, because you're not going to use it so much. So, but in the case of here, so here you're going to consider, how do I call them? T or how do you specify this? Such as, so here in this case, it's real entries, okay? And so here, of course, in this case, when you have only one number, this means that you consider the usual Euclidean metric, but it's what you are used to. Okay, so this shouldn't surprise you. And so now, if we add again a S in front of this O, this means that then you consider the spatial orthogonal group. And so what do you add? You add that the determinant is equal to 1. Okay? So you could also have so here you can also have this kind of group. So SO, depending on the metric you're using, SOPQ or SON, which are special and so which one do you know here? So you should be familiar with SO3. So what is SO3?
3D rotation.
Yeah, so okay, so everyone is okay with that. So it's a group of all rotation in three-dimensional Euclidean space. So you just consider the rotation you all know. So this has the rotation in space. Good. And so I already mentioned this one. So depending on the signature you consider, so 3,1 or SO13, which is so the Lorentz group. And so the Lorentz group here is doing for the Minkowski space what SO3 does for the Euclidean space. Okay, so the Euclidean space, we said that is a group that is going to preserve distances and angles, so it's going to preserve the scalar product. And here, this is also the case for the Lorentz group in the Minkowski space. So, more precisely, if I give you the definition here, at least not the definition, but so it's a group of 4x4 matrices preserving the standard Minkowski metric. Okay. And you can really see SO3 as the set of 4x4 matrices, which is going to preserve the Euclidean metric. Okay? So just the scalar product. And so here, what do you have in this group? You have the spatial rotation. Okay? So spatial rotation plus what we call the boost, which are the Lorentz transformation, which are going to mix up spatial coordinates and time coordinates. Okay, so the rotation are just acting on the space coordinates, and here you are going to mix up coordinates. But again, as I mentioned before, contrary to the Galilean case, now these boosts do not form a group. Okay, so more technically, you could, it's what is called a K-loop. Okay. But so I'm not going to give more detail here. You have some detail a bit in the lecture note. But you know that here, if you look at the multiplication of two boost elements, what you get using the group multiplication of the Lorentz group, what you get is usually a rotation times a boost. Okay, so it's not closed under the group multiplication of the Lorentz group. Then, of course, you could define. It's possible to define another group multiplication, but it's not a group. Another multiplication which won't be associative anymore, and then you could get a closed closeliness using this new multiplication. But since it's not associative, we don't call that a group. Okay, it's what is called a K-loop. So you can have additional structure still. Okay, which group do I need to? So since I'm here, before going to this U, I still need to introduce the U. Let's go to the Poincaré. Again, group. As I said, you are going to study that this afternoon in the tutorial. So we also have the Poincaré group, which is going to be important for you. So what do we have in our list? So we started with general linear group, which are more or less all the matrices which are invertible. then the special linear group, then orthonormal group, and special orthogonal groups. And now we go to the Poincaré group. So the group, this again is a group of symmetry of Minkowski space. That is, it's the Lorentz group plus and translation. Okay. So this means that it's a group that preserves here space-time interval so it's really the group of symmetry of Minkowski space. And any such group element can be written as a product of a translation and a Lorentz transformation. Okay, so to finish with this catalog, the last class of group I want to introduce is the complex analog of the orthonormal group. So orthogonal group are real groups here. Okay, I specify that the matrices have real entries, but you have the analog of this, in the complex analog of this. And the most important one is what we call the unitary group, which is denoted UN. And so these are the group of all unitary n-time n complex matrices. And this is going to preserve the usual inner product of Cn. Okay, so here this one preserves. This is a group of unitary and complex matrices, and this preserves the usual inner product on Cn. Okay, so it's really the complex analog of On. And of course, you have the special unitary group, which is a subgroup of UN, and it's all the unitary matrices which have determinant equal to 1. Okay, so here you add plus det is equal to 1. For special, it's always means the same thing. Okay, and all these groups here are Lie groups. Okay, so any questions here?
How do you find the OPQ precisely?
So OPQ is if you consider a space with a metric with signature. So if you have a metric with, and then with signature PQ. So you see that in the Lorentz case, when I wrote this metric here, the Minkowski case here, the signature is 1, 3. Okay, so here it's in n dimension, so P plus Q is equal to 1, is equal to n, sorry, if it's n dimensional. And then you can define a metric with this signature. So you get the notion of scalar product of length for this space, and then the group which is going to preserve this scalar product, the length, the distances, and the angle are going to be this orthonormal group. Okay. Okay. So this is what I wanted to say about. So these are mainly all the group you're going to see, the main groups you're going to see in the different lectures you will have starting in September. Okay. So now what I want to do is to talk about Lie algebras, okay, and how Lie algebras are related to Lie groups. And for that, I want you to start with a small, maybe try a small exercise to think about how things are going to appear. So we are going to do that together, and then I'm going to give you more technical definition. So you can start. I want you to write the matrices for the three-dimensional rotation by an angle theta. So we are going to choose a counterclockwise rotation about the x-axis, y-axis, and z-axis. Okay, so you can start writing these three matrices if you know how to write them. And from that, I want to show, so these, of course, are going to be group element of SO3. And from that, I'm going to show how you get the generator of the associated Lie algebra. And from this generator of the Lie algebra, how you go back to these matrices. Okay? So here now it's, so you can start, and then I'm going to give you the next. So the first part, so what are the matrices? For 3D rotation by an angle so counterclockwise. So about x-axis, so I want three matrices, y-axis. And then starting from these three matrices, you know that in physics we often talk about infinitesimal rotation. So what are going to be the infinitesimal rotation associated to the three matrices? Meaning you look at the case where theta is going to 0, and you're going to see that this is the way you're going to get the generators of the associated Lie algebra. Then the question will be, second part will be to find so this means that you take theta goes to 0. So you're going to call them Jx. And you just look at the first order theta. And at the end here, you should end up with the generator of the Lie algebra. And then I want you to show that the rotation by an angle about can be obtained by exponentiating. Okay? Your generator Jz, meaning that you want to define your group. So So this is going to give you a group element as the exponential of, and I'm going to write here what is the exponential of an n time n complex. Well, it doesn't have to be complex. But so exponential of m is defined as the series here. So 1 plus m etc. Okay, so do you so I guess you should all know, at least you should find easily online if you don't remember how to get these three matrices. So what do you have here? For the first one around the x-axis, let's say.
You have 1, 0, 0,
Yeah.
0, cosine theta, sine theta, 0 minus sine theta, cosine theta.
Okay, good. Or maybe, yeah, if you choose the counterclockwise, you have the minus here, but it's fine. And then what would you get for around the y-axis? Something quite similar. So what would be the first component?
Sine theta.
I think it was almost. You had the then of course you will get 0 sine here. Then 0, 1, 0, and then you get your minus. Okay, and the last one around the z-axis. So what do you get? Same amount. 0 sine cos 0, 0, 0, 1. Okay. Okay, so this is your starting point now, if you are not there. So what are the associated infinitesimal rotation? So I guess you can give me. So here, how do you proceed to get that? You can differentiate the component of the matrices and then set theta to 0. Okay? So what would you get? What I call
cosine theta to 1 and sine theta to theta.
sorry?
Change cosine theta to 1 and sine theta to theta.
Yeah. Okay, so what do you... No, but then you put theta to 0, okay? So you differentiate. So, and then set theta equals 0 to get here the generator. So what do you get?
0, 0, 0,
Yeah. 0, 0, 0, then
0, 0, minus 1, 0, 1, 0.
okay. And then here, what do you get here?
1.
Okay. Then minus 1, 0, 0. Very good. And the last one, so 0, minus 1, 0, 1. And so what do you get here? These are the matrices in the are matrices in the Lie algebra, okay, that usually of SO3 that is denoted small this. And there are even what we call the generators here of the Lie algebra, and they describe what we call infinitesimal rotation. And so now, if I give you the Lie algebra, so here you started from the group. From the group, you can find the associated Lie algebra. Now, if I give you a Lie algebra, can you find the an associated group element? So let's start, for example, with the this generator. This generator is going to generate rotation by about the z-axis, and to get this rotation by an angle theta, so the finite matrix, okay, not the finite rotation, not the infinitesimal rotation, then you can use the exponential map, okay? So let's try to use this here. So first, so we start from, then, so you need to compute this power of matrices, but here it's going quite easy, because if you just notice that, so what is jz squared here, what do you get? So I want this one. So what is the first coefficient? Yeah, and then
0.
Okay, then
0. Oh, 1.
what is it? 0 and then? And then 0.
0.
Okay, so what does it mean now? This means that it's going to be, if you compute that, etc., and then you will get, of course, is equal to and so on. Okay, so now if you compute this explicitly, you write all the different terms. You can combine them this way. So some term proportional to jz and some term proportional to. So what do you get here? So you will get the theta term. Then when do you get the jz again? It's when you are the cube. So what is the coefficient here that you get? Minus plus, so you get a minus coming from here. Then you get the theta cube, etc. Okay? And here, what do you get? So you get the first term coming from the squared, so it's just. And then you get a minus coming from here, and it's the term to the power 4 plus etc. So what is this expansion here? Do you recognize it?
Sine.
Fine, yeah. And here, what do you get?
Cosine.
Are you sure it's cosine?
Minus cosine.
Yeah, it's, and something is missing, no? So it's,
Minus cosine plus 1.
yeah, plus 1, okay. 1 minus the cosine. Very good. Okay, so here, and so now, if you replace with the component here, you get exactly what you started with, okay? So this means that you get here the cosine maybe there is sine. I did a sign mistake, no?
No, J3 squared is negative. It's like -1, -1. J3 squared.
Yeah, okay. Good. So that's, yeah, that's, okay. So cos theta, then, no, I was, yeah. So the 1 is going to, okay. Be removed, good. So you get the cos theta here, cos theta here, and then the jz is sine minus sine, and then so what we have done here, so I'm going now to give you, to finish, to give you the definition of a Lie algebra explicitly, but this can always be done, okay? You can, given a Lie group G, its Lie algebra can be constructed and you can always go to this infinitesimal level. So I'm going to be more explicit what this means exactly, but starting from a Lie group, there is always a Lie algebra associated to that. Then by reciprocally, given a theorem of, by a theorem of Cartan, we know that any Lie algebra is the Lie algebra of a given Lie group. Then we are going to see that this is not unique. Okay? For example, here we are going to talk about, so we introduced already SU2 and SO3. Okay? So these are the rotation, this is the unitary group, and I told you that this was a 3-sphere. And in fact, these two groups are different. Otherwise, they won't have a different name, I guess. And you will see why exactly what this means are different. But they have the same Lie algebra. Okay? So you can have, and in fact, what is unique is, so I'm not going to give you all this detail, but from a given Lie algebra, you have a unique simply connex Lie group, okay, which is here SU2. And in fact, this is the double cover of SU2. Okay? So topologically, what this means at the topological level, so SU2, we said that it was a 3-sphere. And what is SO3? It's like the 3-sphere, but you identify the two hemispheres. Okay? So you have this kind of identification. And so then why is it not simply connex? So simply connex means that when you have a loop, okay, it's contractible. So this is the case for a 3-sphere. But then this, it's a kind of generalization, more or less, of a donut, okay? Where a donut, you can see that as you have a rectangle. So a donut will be a rectangle where you identify each of the sides of the rectangle. So then you have this non-contractible curve, okay? And it's the same thing, kind of same idea that is happening with SO3, where you have the 3-sphere, and then you identify two same objects, so you will end up with non-contractible curves. Okay, so this was just to give you an idea. So from a Lie group, starting from a Lie group, you can always define the associated Lie algebra. Then if I'm giving you a Lie algebra, you can always find a given Lie group, but then it's not a unique Lie group, okay, associated to a given Lie algebra. Yeah?
What's the definition of algebra?
Yeah, so I'm going to give that good question, and I'm going to give it to you right now to finish. And then we'll see you this afternoon. So what is a Lie algebra? So the definition of a Lie algebra, the first definition, and then I'm going to give more detail of what is an algebra and what is. So the next step is Lie algebra. So a Lie algebra, I'm going to write it explicitly because it's important, of a group G. So usually we use this notation. So is the tangent space of the identity component. So what is a tangent space is a vector space, and the dimension of this tangent space is the same dimension as the group you started with. Okay, so this means that the dimension of your Lie algebra will be always the dimension of your group. And in fact, this is the way we build out here SO3, okay? Because we introduced that as infinitesimal rotation. So we started from the Lie group, and then it's infinitesimal rotation. So you see that here, to get these matrices, what you do is you take your group elements, you differentiate, and then you set theta to 0. So theta to 0 means that you go to the identity component, okay? And so this is the basic definition. So now, what is the mathematical definition of an algebra, to answer your question? Because we have some structure on that. So an algebra A is a vector space endowed with an additional binary operation so that I'm going to denote like this. Which is so that is that we have for any element of your Lie algebra, this is bilinear, meaning that you have this associativity. So the distributivity, so this is a distributivity law. So this is for any x, y, z in A. Then you have the other way. So so this is always this symbol here that I'm using, the star. And what is the last one is by the multiplication by some scalar, the scalar multiplication. So this is lambda theta, and this is valid for any x, y in A, and lambda theta are in K, where K again can be equal to R if you are talking about real algebra or a complex one. Okay? And so this is just the definition, so you won't have to use it so often. And now what do we add to have a Lie algebra? So the Lie algebra is a specific algebra for, where here the binary operation has some additional properties. Okay? So what are these properties? So now the definition, and I'm going to introduce a very important object here. And I'm going to finish on that. And then we're going to use this definition. And tomorrow we'll see what are the Lie algebra associated to the groups I gave you before. Okay? So a Lie algebra, of course, is an algebra for which the bilinear operation that we're going to denote this way, and in fact, it's what we're going to call the Lie bracket. So I guess you already heard about this. Is neither commutative or associative, but is going to follow two specific properties, or two specific properties which are special so it's antisymmetric, so x with y is going to be, so this is really like a commutator, so you know, for all x, y in your Lie algebra. And then it satisfies this Jacobi identity, okay, which is really fundamental here. So what is the Jacobi identity? So you just permute all these symbols plus z x y is equal to 0, and this is what we call the Jacobi identity. And just here this is what we call the Lie bracket. Okay, so this afternoon we have a tutorial, and during the tutorial you're going to study the Poincaré group, and in particular the algebra associated to this Poincaré group. Okay, so you have seen that this Poincaré group is going to be really important because it's the symmetry of the Minkowski space. So you're going to talk a lot about it in the different lecture you will have later on. And tomorrow I will go with that, and I will give you what are the algebra associated with the groups I give you in this catalog. Okay, how do you characterize them? And then we will go back to Lie group for, again, go to the representation theory, and then we will do a specific example with SU2. Okay? So have a good lunch break, and see you this afternoon.